So what properties can we actually figure out about these planets? Remember, in most cases, we can't actually see the planet itself. So what can we figure out about it? Well, we can actually determine the planet's orbital period, that's how long it takes to orbit, the orbital distance, how far away it is from the star, as well as the orbital shape, how eccentric the orbit is. We can figure out the planet's mass, the planet's radius, and the planet's density. And if everything works out just right, we can even figure out atmospheric properties. Does it have an atmosphere, and what is that atmosphere made of? Now, we actually learn different pieces of information from each of the three different methods. And by three, we're talking the big three. So astrometric, Doppler shift, and transit. So all of the three major methods, again, that's astrometric, Doppler shift, and transit methods, are able to determine the planet's orbital period and distance. From the period, we can how long it takes for it to go around, okay? And then from that, we can use Kepler's laws, which tell us the distance of the planet from the star. The astrometric and Doppler shift method also can figure out the eccentricity of that planet's orbit. The astrometric and Doppler shift method can both help us determine the mass of the planet, and that's because both of these methods rely on the gravitational pull of the star or the planet on the star. Okay, remember, we're seeing how it is that the star is moving. In the astrometric, we're actually seeing how it is that the star is moving itself in the sky. In the Doppler shift, we're looking at the red shift, blue shift as the star is being pulled towards and away from us. Now, one important thing to note with the Doppler shift method, the mass that we determine is actually a lower limit, and that's because we don't know the inclination. We don't know how the star system is tipped compared to the Earth. If we're looking at it perfectly edge on, then the mass that we measure is the true mass of the planet. But if the orbit is tilted, then it's only a lower limit. We don't actually know, we only know that it's at least this much mass, it could be greater. The only method that gives us information about the radius is the transit method. A larger planet is going to block more light, and therefore we can figure out its size. Okay, if it blocks more light, it's a bigger planet. If it blocks less light, it's a smaller planet. So all of this is determined by the depth of the light curve. Now, we can't actually determine the density unless we have both the mass and the radius. Unfortunately, that means that we have to use two different methods to get at density. We use the Doppler shift method to figure out the mass, and then we use the transit method to figure out the radius, which then gives us the volume. And with the mass and the volume together, then we can figure out the density of the planet. Okay, now, I just mentioned that the Doppler shift method only gives us a lower limit. However, if we actually see a transit, then that system has to be edge on. So we can be fairly confident that we actually have the planet's mass. Now, during a transit, it may be possible to actually look at chemical composition. So specifically, we look at the spectrum. So what we do is before the transit, we get the spectrum of the star, so we know exactly what the star's spectrum looks like. Then, when the planet crosses in front of the star, some of that starlight will pass through the atmosphere, if there is one, of that planet. And that is going to put a different absorption lines onto the star's spectrum. So any new absorption lines that appear, we know have to be coming from the planet. So in this way, we've actually been able to find planets with atmospheres, usually Jovian planets, having a lot of hydrogen and helium. However, we've also found water vapor. Now, this is water vapor on a Jovian planet, so we're not talking about life here, but it's still exciting. We have yet to actually detect an atmosphere on a terrestrial planet. That's because the atmosphere of terrestrial planets are much thinner. But we are advancing all the time. So I wouldn't be surprised in the next few years if we actually start getting data on atmospheres of terrestrial type planets orbiting around other stars. Now, it may be possible to figure out the temperature of a planet. One way we can do it is just through the equilibrium temperature, how much of the how much light is the planet receiving from its star compared to how much is it able to give off. However, if we look in the infrared and the planet is hot, the planet itself will be glowing. So when we have a eclipse where the planet goes behind the star, then we can see a dip in the infrared light, and the amount of dip in the infrared light is how much infrared light the planet is giving off, which is then going to be related to the planet's temperature. Doing something similar to this, we've actually found a planet that has a surface temperature hotter than the coolest stars. In other words, this planet is literally red hot, which is awesome and kind of terrifying. All right, here's a thought question for you. Suppose you found a star with the same mass as the sun moving back and forth with a period of 16 months. What can you conclude? A, it has a planet orbiting at less than 1 AU. B, it has a planet orbiting at greater than 1 AU. C, it has a planet orbiting at exactly 1 AU. Or D, it has a planet, but we do not have enough information to know its orbital distance. Go ahead and think about it, and we'll discuss in just a bit. All right, so we're going to have to start applying some of the things, not just from this chapter, but what we've learned before using Kepler's laws. So let's start with the sun and the Earth. We know that the Earth orbits around the sun every 12 months, and that the Earth is at exactly 1 AU. Because we know that the star has the same mass as the sun, then it's going to be a very good analog to our own solar system. So the Earth orbits around the sun in 12 months at 1 AU. Kepler's third law states the farther away the planet is from the star, the slower it orbits, or the longer its orbit is going to take. So this planet has an orbital period of 16 months, which is greater than 12 months. Therefore, it must have a larger orbit. So the answer is B, it has a planet orbiting at greater than 1 AU.